asked me to give this talk instead. There's actually John and I are good friends, but we have a slightly different slant on this. So now without him here, I can get to do my own thing. So my question was how all electrolytes fit in the Stewart equation. So Peter Stewart created an acid-base analysis that included all components of the solution, a physical-chemical approach. Basically, something happens between our physical chemistry courses we take and our organic biochemistry, really biochemistry, and we seem to drop the physical part. I'm not quite sure why. What I'm going to emphasize today is not the full Stewart approach, because I can't do it in this time, but I'm going to emphasize the electrolyte elemental part and the key role that hydrogen ion is determined by the difference in charge of strong positive and negative ions, which is what we've been talking about today. So basically, I'm going to talk about the importance of water, what is an acid solution, the role of strong electrolytes, clinical disorders, and just a little bit on a clinical approach. So let's begin with hydrogen ion. Why is it so important? Well, the concentration of hydrogen ion affects the interactions of hormones, drugs, plasma proteins, cell surface receptors. It affects the structures of proteins, their tertiary structures, and enzymatic function. And so for this reason, it's very tightly regulated right throughout the animal kingdom. Basically, all organisms have pHs in their cells that's somewhere around 7 to 7.4. And hydrogen ion is so important because you have the most highest charge density of any element, because it's just a single positive proton in the middle versus anything else that has neutrons and protons, so they decrease the charge density. So that charge density makes it very reactive. Now, a surprising point is that water is the most concentrated substance in living systems. It's 55.3 H2Os per liter of water. So in the next closest in plasma is sodium at 0.14, so over 100-fold times higher than anything else. So it's a very concentrated solution of the molecule H2O. Only a small amount of that dissociates into hydrogen and hydroxyl ion. So at water at room temperature, standard temperature pressure is 100 times 10 to the minus 9th moles. Pretty small number. However, you should appreciate that at 7.4, the concentration in your blood is 40 times 10 to the minus 9th, which means a beaker of water has over 2.5 times as much hydrogen ion in its concentration than actually your blood does. We'll come back to that. Now, pure water at body temperature has a pH of 6.81 and 150 millimoles of hydrogen ion. So in other words, almost 4 times the amount you have in your blood. My question is, so if it's 6.8, is this an acidic solution? And the answer is no, 6.8, but it's not an acidic solution. So we have to go back to what is an acidic solution. Now, I'm not big on the Lowry, Bronsted, Lewis definitions, and I really like the older Arrhenius definition, and that's what I'm going to use. And I think the reason why this is the one that we need, the others were made to be universal and all kinds of solvents. But in biology, we deal with water, and the Arrhenius definition deals with water, is what we deal with. And then it becomes much simpler. So an acid is a substance that increases hydrogen ion concentration. A base is simply a substance that decreases hydrogen ion concentration. An acid solution is one in which the hydrogen ion is greater than the hydroxyl ion. A basic solution is one in which the hydrogen ion is less than the hydroxyl ion, and a neutral solution, they're equal. So let's go back to the pure water. When you warm up water, the dissociation constant increases. So if we start off at room temperature, well, a little warmer than room temperature, 24 degrees, we have the standard temperature pressure and a pH of 7.0. But as we heat up the water, the dissociation constant changes. So if we look at this with a pH and a hydroxyl ion, hydrogen ion, we start off at 24 degrees and we have a pH of 7. If I now warm up to body temperature, 36.7, I now have a pH that's around 6.8, but the hydrogen ion and hydroxyl ion are still equal, and so it's a neutral solution. So the first message for you is pH does not tell you whether it's an acid solution. That has nothing to do with that. It is simply telling you the hydrogen ion concentration. We've defined an acid solution and one in which the hydroxyl ion is greater than the hydrogen ion is greater than the hydroxyl ion. Now, as I said, a pure beaker. Wow. So as I said, a pure beaker of water is 6.8. It's not an acid solution because the hydroxyl ion and the hydrogen ion are equal, and the dissociation constant changed. So why are inorganic, or basically elements, electrolytes, so important? Well, they regulate osmolality, as we've heard today. They affect transmembrane potentials, especially potassium and sodium. And this other one, acid-base, which I'm going to review now. And the way they do these is by creating two forces, an osmotic gradient and electrical charge. And the one that's really important for acid-base is the electrical charge. I reviewed these in a recent paper that came out in Best Practice in Research in Clinical Anesthesiology, specifically talking about balanced salt solutions in chloride, which we've heard about today. So let's get into what is a strong ion. A strong ion is an electrolyte that's always completely dissociated in a solution. Well, it's not completely, but essentially always. You're dealing with more than 1 in 10,000 that's bound. So essentially all of it's dissociated. So if we look at a beaker of water that has sodium chloride in it, you don't have sodium chloride. The positive ones first. So sodium, potassium, calcium, magnesium, the things we've been talking about today. And on the negative side, chloride, sulfate, lactate, beta-hydroxybutyrate, formate, oxalate. Not phosphate. Phosphate's actually a weak acid. So in this solution, you don't have sodium chloride. You have a sodium ion and a chloride ion. They dissociate. You do not have them together. The reason why this is important is these are charged elements, and if there's a difference in their concentrations, they're creating a very important electrical force in the solution. So what about the osmolar contributions of different parts? So this is serum, interstitial space, and intracellular space. So sodium in the green, making up the large chunk on the positive side, chloride, bicarbonate, and then a bunch of other things which are smaller. Interstitial space, almost the same, but we leave out the protein, the albumin component, which is much smaller. And inside the cells, potassium takes the place of the sodium, and chloride, which becomes very small, about 10 millimoles inside cells. Okay, so the key point about the charge is this principle of electrical neutrality. So in a macroscopic sample of an aqueous solution, the sum of all positive charges have to equal all negative charges, and I'm going to show you why. So if we start off with a sphere that's 1 millimeter in radius, tiny little thing, and you have a charge difference of 1 times 10 to the minus 7th. So think of it, we're usually dealing with 10 to the minus 3 in terms of potassium and sodium. So 1 to 10 to the minus 7th, okay? 10 to the 4th fold smaller. Really little charge difference between the inside and outside. You can calculate the volume, which is 4.2 times 10 to the 6 liters. Then you can look at the net charge, 4.2 times 10 to the minus 13th equivalents, pretty small number. But then you multiply it by Coulomb's number, and you can work out the charge in volts. And this little sphere, with that tiny little bit of charge difference, works out to a voltage of 400,000 volts. Now, it's a snap. It's like when you touch your finger and you get a charge. But it's a huge electrical force that has to be dissipated. And that's 10 to the minus 7th. We're dealing with 10 to the minus 3. You can't have it. You can't have it. It's got to be dissipated. So the charge from that difference of strong electrolytes, they create a force which affects the dissociation of weaker substances. Water, as I've already discussed. No, I haven't actually, but it'll affect the dissociation of water. Carbonic acid, so PCO2 to carbonic acid, which is also a weak volatile acid. And in serum, or in the blood rather, and plasma, albumin, which is also a weak acid. So the dissociations of those are affected by the strong electrical force. And that is what determines the hydrogen ion concentration, because these are all dissociating to hydrogen ion. Now, this can be looked at by this diagram out of Stewart's original book. And what you have on the y-axis is hydrogen ion and hydroxyl in equivalents per liter, and the difference in charge between the positive and negatives. So I'll break this down. On the left side, you have the negatives greater than the positives. So chloride greater than sodium. On the other side, you have the negatives greater than positives. The key point is when you have more negatives than positives, in other words, a negative strong ion difference, for whatever change you make in the negative charge, like if you gave hydrochloric acid, for example, as you added the chloride, you would get a 1-to-1 change in the hydrogen ion concentration. But when you're on the side where the sodium is greater than chloride, it's completely different. What you then see is a much smaller change in hydrogen ion for any change in the strong negative, such as chloride. So on the left side, it looks like when you added the chloride, you added a hydrogen ion. It looks like the hydrogen ion was an independent variable. But it becomes very clear on the other side, it is not. The other important point, these are alkaline solutions. You can see the hydroxyl ion is much higher than the hydrogen ion. So when you have a sodium greater than chloride, it creates an alkaline solution. As it turns out, all body compartments, with the exception of your stomach when you're fasting and lysozymes, are alkaline solutions. You never actually have an acidic solution in your body, even when you're almost dead at a pHs of 6.8 or so. Now, this actually is a valuable component. I told you hydrogen ion is very important to affect other molecules. So by having smaller changes and being alkaline, from an evolutionary point of view, that means that we weren't getting as big disturbances every time we moved an electrolyte. If we were on the other side, every time a sodium moved in and out, it would have a much bigger change on hydrogen ion and a much bigger change on many of the proteins in our bodies. So from an evolutionary point of view, this makes a lot of sense. Now, we talk about exchanges between sodium and hydrogen, potassium and hydrogen. These are six-fold differences. What does that mean? I've actually calculated. It's like taking the Empire State Building and exchanging it with an ant. You can't do that. I mean, you just can't. So it looks like they're exchanging, but the orders of magnitude difference. What you're doing is changing the characteristics of the solution, which affects the dissociation of water. Now, the major players of the SID in normal plasma are sodium and chloride. And so we can actually really reduce this analysis to sodium and chloride because the others don't change much. Here again is a gamblegram of plasma with cations and anions, so the prominent sodium and the prominent chloride, and then bicarbonate and the protein effect. So the potassium, magnesium, and calcium, very important. I don't want to put them down for the other functions, but for acid-base, they can't change much. If you change your potassium by 2 milliequivalents, you could be dead. You change your magnesium by 2 milliequivalents, you're dead. So they can't really change much. So we can basically ignore this, and the analysis becomes much easier because we just can concentrate on sodium and chloride because that's what the body really has to play with. Actually, go back to that. So this part here is the strong ion difference, which is accounted for by the effect of weak proteins and bicarbonate as the other component. And the anion gap really just being related to the part from the protein. So some simple guidelines: if you increase the sodium relative to chloride, it's like adding sodium hydroxide. It's an alkalinizing effect. And if you increase the chloride relative to sodium, you narrow that difference. It's like adding hydrochloric acid, and it's acidifying effect, although you actually never create an acid. I'm going to skip that for the sake of time. So what can the body use to regulate hydrogen ion? Well, sodium has to be kept constant to regulate volume, so you really can't play with that much. I mean, it does alter, and we heard that in the first talk, but it's not going to be a good regulatory mechanism for long-term management from an evolutionary point of view. Protein concentrations also have an effect, but they're important for oncotic pressure, and again, that's not something the body is going to purposely use to regulate. So CO2 is used, and you get the rapid adjustments with getting rid of carbonic acid by blowing off CO2. But anything else is really chloride. So that's why chloride becomes so important in the system. This is really the major regulator of a metabolic process. You don't have any other opportunities with normal things in blood. So chloride is the major factor. Now, let's see how this can be altered by some simple things. I'm going to be running tight, so I'm going to have to shorten. So one of them is a water effect. Let me start off with a beaker of water with 140 milliequivalents of sodium and 100 of chloride. So the difference is 40 milliequivalents. If I double the amount of water, I will now have a reduction in the concentration of both sodium and chloride, so the difference is only 20. And because I've reduced that difference, that will alkalinize, that will acidify the solution. I'll reduce the strong ion difference. It's more alkaline, or becoming more acidic is the other way to look at it. How does this happen? Like, where does it come from? Well, remember I added water, which actually had greater hydrogen ions than my original solution. So that's how the conservation of mass is maintained. So simply changing the water in the beaker of a salt solution will change the pH without a kidney, in all fairness to my nephrologist. This happens in a beaker. So this is the cause of a hyponatremic acidosis. On the other hand, we already heard about this, so I'll be brief on it, but as you add sodium chloride, what's happening, you're adding a solution with equal sodium and chloride, and by doing that, you're narrowing the strong ion difference, and you're acidifying the solution by narrowing the strong ion difference. Furthermore, it's harder for your body to excrete chloride than it is to excrete sodium. Sodium it dumps easily. To excrete chloride, to excrete chloride, you have to have something else going out with it in the kidney besides sodium, otherwise you haven't changed it. And I won't go through this in detail, but it's in my chapter. But you basically have to make ammonium chloride, and it's ammonium rather, and the ammonium as a positive ion then can go out with the chloride, and that takes time. If you don't do that, you have to dump out sodium and potassium, and you can really deplete your intravascular volume. Lactic acidosis. So in lactic acidosis, what's happening is you're adding a strong anion, lactate, and by doing that, you're narrowing the strong ion difference. So before, the strong ion difference was made up by two weak substances, the albumin and the bicarbonate, but now you added another strong one, so you narrow the strong ion difference. It is identical to giving more chloride. So that's what creates the acidosis or acidemia with lactate. So the only way you can fix it when you're giving bicarbonate, I put in quotations, because you don't give bicarbonate. You give sodium bicarbonate. And what the sodium does, it re-widens the strong ion difference, and that's how you correct it. But not for long, because your kidney likes to keep its sodium at a fixed level, and it'll dump that sodium, and that's why you can't fix a lactic acidosis with sodium bicarbonate. You will transiently, but not for long. And the CO2 part is regulated by your brain that keeps PCO2 constant. So how do you use this clinically, just to wrap up? Well, John Kellum has what he calls the strong ion gap, which he adds up all the positives, and then he looks at the parts due to CO2 and albumin and phosphate, looks at the difference, and that's something missing. But you really don't need all these. I just find this too complicated. So we used an approach using base excess. So base excess, that little thing on the blood gas, when I was a medical student, I remember one of my classmates putting up his hand saying, "What's base excess?" And the prof saying, "It means nothing, ignore it." Well, it's actually quite a neat thing. What it was is Sigurd Andersen did the titrations on normal blood with strong bases and strong acids, basically equivalents of hydrochloric acid and sodium hydroxide. That's not what he used, but basically strong ions. And he did the titrations. So the base excess matches very closely the strong ion gap that John uses. So we take the base excess off the blood gas and use that as a guide to the metabolic components of an acid base. So the approach is basically we look at water effects by looking at the dilution of sodium. We look at chloride effects after correcting for the chloride part, so we get a chloride effect. Then I look at an albumin effect, which I haven't discussed today, but the effect of the amount of albumin. I compare that to the base excess to find out what's missing, which are essentially the anion gap, wide anion gap acidoses. I've actually created a phone app for this, which is available free if you search it on my name, Magder Acid Base. It's got some glitches yet getting fixed, but it's free. It's only on iPhone now, but it will be coming out on Android soon. And you can just enter the values with that. The phosphate is not included in the other. I add it after. So you put those in, and then it calculates the others, and you also get the phosphate effect. So you can look at a water effect, a chloride effect, an albumin effect, and then you direct your therapy. If it's a water effect, adjust the amount of water relative to sodium. It's a chloride effect, change the solution. Albumin, Well, I don't think you have to correct that, but at least you know that's the cause. And the others are the typical wide-ionic gap acidosis. So it gives you a pragmatic, practical approach using the physical-chemical principles at the bedside. So in summary, water is an important source of hydrogen ion. The strong ion difference provides the major force which determines the hydrogen ion concentration in water. Chloride is the major ion the body can use under physiological conditions. And finally, the metabolic components of acid base at the bedside can be considered water effects, chloride effects, albumin effects, and others. Thank you.